Good afternoon, everyone. Today, what we're going to do is continue our discussion of Chapter 13, looking at two-way ANOVAs. And in particular, we're just going to work through an example. And then at the ending, we will start looking at some of the material for Chapter 14. Just for your information, the Chapter 14 is not in the hard copy of your textbook. It's a companion chapter. Those of you who have Launchpad or have registered, you can access it there. But I have also uploaded a PDF of Chapter 14 on CourseLink so that you can read through the material on your own and work through the exercises there. Okay, so last day, what we did was we looked at two-way ANOVA, how we actually set up the ANOVA table, calculating some of the sums of squares in the special instance where we have replicates um, of our basic design, and we talked through how you could perform tests for the interaction effect as well as main effects. What I wanted to comment on is that you can uh, do contrasts or look at specific contrasts and multiple comparisons to compare not only specific cell means, but also the marginal means of a two-factor experiment as the way we did for a one-way ANOVA. However, I just wanted to note that we won't go over this in detail in this course. So not um, needed for this course. But it's good to know or to be aware that you can actually do these. So the example that I wanted to work through is exercise 13.40 in your textbook. It's on page 722 and it's on iron content. So this study was interested in looking at, or sort of the big picture concerned iron deficiency anemia because that's the most common type of malnutrition that's seen in developing countries. And from a public health perspective, the idea was what is a good way that we could try to increase the iron intake of people in the developing countries, with the thought that a lot of these countries, the a good chunk of the proportion of the population don't necessarily have a lot of money to go out and buy supplements and such like that. So one theory was that the food that is cooked in iron pots increases the iron content in the food. And the investigators wanted to go out and test that theory. So, a little spoiler alert, the cooking in an iron pot or dish does increase the iron content. Just sort of as a sort of personal story, when I moved back to Guelph or to Canada from Singapore. I used to work there at the National University of Singapore. I was involved in some, or I had more exposure to studies that were done in developing countries. And one of the big ones, particularly for women in sub Saharan Africa, that I had learned about was that they were asked to boil their water in an iron pot, just for this reason to improve the iron content. And I grew up in a family where we cooked with an iron cast pan quite often. But as an adult, I stopped doing that because the iron pan is so heavy, and then cleaning it is a little bit more cumbersome compared to, say, an aluminum or stainless steel dish. But when I came here, particularly in one of my pregnancies, I had very low iron. And so I actually started, pulling out my iron cast pan, and I cook in it fairly regularly now. So let's look at this particular study. It was performed in a factorial arrangement to test this theory of whether the food cooked in iron pots increased the iron content in food. There were three pot types that were considered: aluminum, clay, and iron, and three food types: meat, legumes, and vegetables. So by factorial arrangement, that means that all factor combinations were tested. And the actual response was the iron content, where the specific measurements was the milligrams of iron per 100 grams of cooked food. So, when we get data from this type of study, there might be three particular questions of interest. Is there, now I think I corrected the version of these notes that are posted for you, but is there an interaction between pot type and food type? Is there an effect of pot type on iron content? And is there an effect of food type on iron content? So let's look at some of the raw, or let's look at the raw data from this study and see how we can go about constructing the ANOVA table for it. Here's what some of the raw data look like. I'm going to try and zoom this out to see if I can fit the whole table on there. So this is on page 151. And what we can see is that we have our three pot types. Remember, this was the sort of treatment of interest, but the iron uptake in the food might depend on the food itself. So we also considered, or the researchers considered, meat, legumes, and vegetables. And from this data set, what we can see is that for each factor combination, we had four replicates. So that's four replicates per pot type, uh, food, food type combination. So altogether, there are 3 times 3, 9 different factor combinations times 4 replicates per combination. So in total, again, when we put this into our, and I'll call this factor A, and this one will be factor B. So when we try to correspond this back to our notation, we have 3 different pot types. So capital I equals 3 different food types. So capital J equals 3. And then the sample size in each cell, Nij, is a constant, which is 4. So we have capital N equals 36. And this is, we get by 3 times 3 times 4. And if we take the raw data, calculate the standard deviation, then we would get S sub x being 1.075357, etc. So this is the standard deviation of the raw data. Now, once we have the standard deviation of the raw data, then we can calculate our sum of squares total, which is capital N minus 1 times Sx squared. And we find for these data, we get a sum of squares total being 40.473756. Okay, so what would be the next step? If we were working through this by hand, and what's also, I guess, useful in looking in terms of summary statistics is to calculate our table of means and then take a look at that. So the table of means, and see, maybe I can make this a little bit bigger. And from what you'll see in today's lecture is that I've often rounded to 3 decimal places just so we can save space. But again, we have our pot type, which is factor A, our food type, which we can consider to be our factor B, and inside what we have are the cell means. Okay, so um, the X bar IJ. So we can say um, cells contain X bar IJ. Cell means. Because remember that for each combination, so if we looked at pot type aluminum and food type meat, we had 4 different observations. So this 2.058 is the average of all the iron contents from the 4 replicates. Okay, and 2.178 would be the average of the 4 replicates where pot type equals clay and food type equals meat and so forth. In the margins, we have our marginal means. So up here would be the pot type means, and the notation we've been using is X bar I. Across the bottom row, we have the food type mean. So that's our X bar J. And so 2.972 is the average of all observations where food type equals meat, regardless of what the pot type is. Okay. And then, of course, this 2.5451 is our grand mean or our overall mean. And if we wanted to calculate our sum of squares using this table of means, it simplifies because we have a constant number of observations in each cell. We always have 4 um, observations. So we can look at our sum of squares A. Let me see if I can try and keep the 2 of these together there so we can still see. And what we can see is that we get little n, which is 4, the number of replicates, times capital J, 3 different food types, and then 1.873. So this mean minus the 2.5451. Oh, and all of these should have been, um, let me double check. This may have been actually 541. I'll double check that, but it should be your overall mean plus 2.037 minus the overall mean plus 3.713 minus the overall mean. So here we have the sum of the pot type means minus the overall mean. If we want to calculate the sum of squares for factor B, we would do the same thing. I'll try and move this up so that we can see. And what we're going to do is take little n times capital I, and then the sum of the food type means minus the gram mean. So this 2.972 minus the 2.541 plus 2.824 minus the 2.541. Again, as I mentioned before, all of these values are rounded off. So when you do your calculations, you shouldn't round off. But there are only 3 of these terms in the sum, and you end up getting something like 9.297 and so forth. For the sum of squares A, we got 24.894 and so forth. So this sum of squares B, we looked at the food type mean minus the overall mean. And then to calculate the sum of squares interaction, If we were doing this by hand, then we would have to calculate the sum of squares model and then calculate it by subtraction. So I'm not going to go through the nitty-gritty details, but do remember that the sum of squares model is the sum over I, sum over j, and then we have our x bar ij minus x bar squared. So it's the cell means minus the overall mean. So when we calculate that, we can subtract the main sum of squares for A minus the sum of squares for B, and what we're left with is what we call our interaction sum of squares. Okay, so once we have all our sum of squares, we also know what our I, J, and capital N are. We're in business to build our ANOVA table. So let's move on to the next page and do that. Here's what the ANOVA table looks like. Under source, we have the pot type, the food type, the pot by food, and this is our interaction term. And again, this should be corrected on your version, the one that I posted. But for pot type, we have I minus 1 degrees of freedom, which is 3 minus 1, giving us 2. Food type had 3 categories, so there are 2 degrees of freedom for food type. For the interaction, remember that for that one, we had to look at the product 2 times 2. So I minus 1 times j minus 1 gives us 4. The total degrees of freedom was capital N minus 1, so that gives us our 35. And then this one is by subtraction. Okay, so here we have 35 minus 2 minus 2 minus 4 is equal to 27. These are the sums of squares we calculated on the previous page: 24.894, 9.297, 2.640. And we had calculated the total sum of squares. So the 3.643 we can calculate by subtraction. And then we're in business because the mean square is always the sum of squares over degrees of freedom. So that gives us 12.447. For food type, it's 9.297 divided by 2, which gives us 4.648. The interaction has a mean square of only 0.66, but then the error sum of squares is 0.135. So this is equal to our mean square error, which is equal to our SP squared. Okay, and what about the F statistic? Remember, these are looking at our mean square divided by mean square error. Okay, so um, we end up getting, 12.447 over 0.135, for example. This one would be the 4.6 over 0.135 and so forth. And now that we have our ANOVA table, we can actually perform hypothesis tests for the interaction and for each of the main effects. So let's go through how we actually do that. For the interaction test, our null hypothesis is that there is no interaction between pot type and food type, whereas the alternative is that there is an interaction between pot type and food type. Our F statistic is equal to the mean square of the interaction, so AB, divided by mean square error, and we can just read this off the table. So this we can read off ANOVA table. The degrees of freedom is 4 and 27. We can also read that off of our ANOVA table. So there's our test statistic, 4.893, and we can see that it was based off of 4 and 27 degrees of freedom. So that's our degrees of freedom AB, degrees of freedom error. And then calculating our p-value requires us to use table E, look up for 4 and 27 degrees of freedom, where F is greater than or equal to our statistic, 4.893. And what we see is that our p-value lies between 0.001 and 0.01. So the conclusion is that um, particularly at, and I'll make this comment out here, we'll use alpha equals 0.05 throughout, but we can see even at the 1% level, we have sufficient evidence to reject H naught. In this case, we can conclude that there is a significant interaction between pot type and food type with respect to their effects on iron content in the cooked food. So we know that there is an interaction. We don't necessarily know what the nature of the interaction is. That's yet to be determined. What about the main effects? So let's look at the main effects and then we'll see what we can get from those from an interaction plot. So if we wanted to do a test on our factor A, which is pot type, remember that was the treatment of interest or factor of interest, our null hypothesis that there's no main effect of pot type on the iron content of the cooked food versus the alternative that there is a main effect of pot type on iron content in cooked food. Our F statistic can again be read off of from the ANOVA table, 92.263. Our degrees of freedom are 2 and 27. So this is the degrees of freedom A, degrees of freedom error. Our p-value is calculated by looking up the probability that that an F that follows a 2, 27 degrees of freedom uh, is greater than or equal to our observed test statistic of 92.263. And from table E, we get that the p-value is less than 0.0001. So this is highly significant, not surprising. Look how large our F statistic is. So the conclusion is that we reject H naught and conclude there is a significant main effect of pot type on iron content. So if there's a main effect of pot type on iron content, that's telling us that at least one of the aluminum, clay, or iron pots um, have different or have iron content that's different from the other ones. What about food type? So our null hypothesis would be that there's no main effect of food type, whereas the alternative would be that there is a main effect of food type on the iron content in the cooked food. And our F sub B, so our test statistic, would be the ratio of our respective mean squares. We can read that off of our table to be 34.456 and so forth. This is also on 2 and 27 degrees of freedom, but here that's just because we had the same number of levels in factor A and factor B. So capital I equaled capital J, and that's why we get the same degrees of freedom. So it's the degrees of freedom associated with factor B degrees of freedom associated with our error. Again, we can read this value and that value directly off of our ANOVA table. And then the p-value is just the probability that a random variable f that follows a 227 degrees of freedom is greater than or equal to our observed test statistic of 34.456. And again, with table E, we have significant result that the p-value is uh, less than 0.0001. So we can reject our H naught and conclude that there is a significant main effect of food type on our iron content. Again, we've looked at these two main effects, concluded that there are both main effects do exist or are significant, as is the interaction effect, but we haven't actually looked at our data. We could have looked at the table of means, and that would give us some idea as well. But the interaction plot gives us a nice pictorial view. So let's look at our interaction plot. So this is page 155. And what we can see looking at this is that these two lines are very close to each other and um, fairly similar, right? Fairly parallel to each other. So, we know that I've listed a few comments here. What I'm going to do is um, go back and forth between the comments I make on the bottom of the slide, as well as actually, you have the comments, so you can perhaps read through them while we discuss this. So, our test suggested that there were significant main and interaction effects. We just didn't know what those were. If we look at these ones for clay and iron, they're fairly parallel. This gap is fairly small. So the gap that we have in here is a and we also see that the legumes, now the ordering of these dishes or the food type was listed in this way just because the software automatically puts legume first because L comes before M, which comes before V in the alphabet. So that's the only reason they're ordered in this particular way. But what we can see is that legumes are the highest, meat is a little bit less, and vegetable seems to be the lowest. It has a little bit more of a dip. But interestingly enough, the iron pot looks very different. That profile looks different from the other two. We didn't go through and remember we talked about doing multiple comparisons and specific contrasts. I wouldn't be surprised if the clay and aluminum were not significantly different, but that together these were significantly different from iron. In particular, what we can see, there was this little elbow here, but in the iron one, not only are all three food types much higher gap, much bigger gap between those, but then we also see that meat has the highest mean iron content in the cooked food. So this suggests that for whatever reason, maybe because meat might already be high in iron, and then when it's cooked in the iron pot or the iron pan, it's able to absorb more of the iron, regardless of what the um, chemical or physical mechanism. The the meat seemed to have a higher mean iron content. The vegetable was still the lowest, but regardless, all three were much higher than the other ones. So it's very interesting to look at the interaction plot. Actually would have been interested to see, almost as a control. of having a fourth group that was just water, where you can see what's the difference in the iron content in that water. Uh, okay, so that pretty much ends our discussion of two-way ANOVA. When we looked at the full two-way ANOVA, remember the main difference compared to the randomized complete block design or the replicated randomized complete block design is that we actually include the interaction effect in our ANOVA, because we're actually interested in whether there is that interaction there or not. Um, what I wanted to move on to now, and we'll just talk about this briefly. It won't we don't have a lot left to say, but I wanted to sort of get the idea percolating in your minds as you're going through the material. The last chapter of this book, can you believe it? From September till now, you've gone through every chapter in this textbook, plus the supplementary or companion chapter. But uh, chapter 14 goes back to looking at a binary outcome. So in chapters 12 and 13, we looked at the relationship between a quantitative response. So, for example, the mean iron content, and what's its relationship between with one or more categorical variables. But what if our response itself was binary? It wasn't quantitative, and it only had two categories, either a success or a failure. What can we do? Also, I wanted to reiterate that the textbook chapter is posted on course link. So the first point to make is that when we are dealing with a binary response, we often talk about the odds. So the odds of something happening. These odds are based on probabilities, but they are not probabilities themselves. So consider this example from gambling where there's a bet made and you wanted to calculate the odds against winning. In other words, the odds of losing. Suppose the probability of losing is zero point 0.6. If the probability of losing is zero point 0.6 and we assume no ties are allowed, then the probability of winning is 1 minus zero point 0.6. So no ties or draws allowed. Then our probability of winning would be zero point 0.4. Fine. Then how do we calculate the odds? The odds against winning, or the odds of losing, is zero point 0.6 divided by zero point 0.4. So it's just the ratio of our of losing to winning, and that would give us an odds ratio of 1.5. Let's look at this at a different perspective. Suppose we're told that the odds of losing, or the odds against winning, is 7 over 5. And that is equal to 1.4. So it could also be written as 7 to 5 as well. Okay, if we know that the odds is 7 to 5, then that is telling us that the probability, because this is the odds of losing, the probability of losing is just 7, so our numerator, divided by 7 plus 5, or 7 over 12, which gives us a probability of losing of 0.58333, etc. The probability of winning, on the other hand, would be 5 divided by 7 plus 5, or we could think of it as 1 minus 0.58333. Either way, you would get a probability of winning of 0.41667. So What is this telling us about odds ratios in general? When we calculate our odds, it's a ratio of very specific probabilities. In the general setting, we would consider a particular event of interest. So it might be that um, y equals 1 if event occurs, 0 otherwise. And then the odds is just the probability of that event happening divided by 1 minus the probability of the event happening. So, as an example, think about tossing a fair coin. The event of interest might be that the coin lands on tails face up or face up tails. So then, if we wanted to calculate the odds of getting a tails, we would want the probability of tails divided by 1 minus the probability of tails, which would just be is a fair coin. So that's telling us probability of heads equals probability of tails, which equals 1/2. So it would just be probability of tails over 1 minus probability of tails. So zero point 0.5 divided by 1 minus zero point 0.5, which gives us an odds ratio of 1. When we know that the odds ratio is 1, we could also backtrack and say, okay, then the probability of tails would be 1 over 1 plus 1, which equals 1/2, which equals 0.5. Okay, so this is saying the odds, then you have tails to heads is equal to 1 to 1. And then in that scenario, it's easy to see how we come up with this probability of tails. And of course, the probability of heads would be 1 minus that. Okay, so I just wanted to get your brains kind of percolating on this idea of odds. And what we're going to do is compare, or not compare, but combine this idea of thinking about the odds of an event happening with um, regression. And this leads us to something called logistic regression. So, next day we'll talk about that more. But we will probably do, I will also try to do somewhat of a review. It's been a long few weeks since test 2, or a lot has happened. So, we'll go through a review in preparation for test 3. Please stay or continue looking at the announcements on course link and on in your emails. I will be posting more information about test 3. In particular, I have gotten some of the feedback from you about how long it's been taking to scanning for scanning and such. So I will give you more specific times about when I will actually release the PDF for test 3 and the timing to upload it, as well as a little bit more information for those of you who are in SAS. Okay, but again, if you have any concerns still, and if you have tried using the phone app and that does not seem to work for you, please continue to email me or post on course link and let me know how you're doing. Okay, take care. See you next time. Bye.